to the left, you see the switch yard with the coal unloading facility, rail unloading for coal and limestone, coal storage facility, reclaim, conveyors up to the boiler facility. Coal being received by bottom dump rail cars. The cars are positioned by a car puller, unloaded to underground hoppers. Material then is transferred by belt conveyor up to a transfer point where the material can either go to the boiler directly or stacked out to a storage area. Material then can be reclaimed from the storage area and transferred back onto the conveyor system and transferred then onto the boiler. As you can see, some of the coal is a little bit larger size, probably 4 to 5 inch.
Conventional crusher mechanical feeder system, this mill would probably be shut down now because of the moisture content, both surface and inherent, in this type of coal feed. We're told it's running 18% moisture as you see it now. This system is designed to handle about 15% moisture, which means we could use a little bit of auxiliary heat.
The coal bunker, and the coal bunker has air cannons on it, and at the base of the bunker, at the discharge, we have a vibrating bin discharge. Bin discharges to a downshoot with a shutoff gate, and then directly down to the stock feeders.
This then is the low-pressure gravimetric feeder that meters and measures the coal into the DFM mill located on the floor below. At the present time, the feed rate is 10.2 tons per hour. Fuel preparation for the new fluidized combustors has proven to be a significant problem. Moisture contents of up to 15% to 20% can and do cause binding and plugging in primary and secondary reduction in fuel feeding apparatus. The fuel is fed by means of a standard weigh belt or gravimetric feeder in the 2x0 format, containing normal moisture contents of up to 18 to 20%. The pulverizer reduces and dries the fuel to a product size desired. The final product size can be changed while in operation. Limestone is also fed into the center of the DFM system.
Yeah, the limestone is transported by rail car to the plant, stored in that concrete silo. It is transported to silos inside the boiler house for injection into the CFP boiler combustor.
The limestone sorbent is recovered from overhead storage by means of a vibratory output conveyor at the bottom of the bin. This product then drops down into a variable speed screw conveyor, which takes the pre-sized dried limestone and meters it into the center of the DFM mill located on the floor directly below. sorbent demand is a direct function of the SO2 as being measured at the outlet of the stack. Mixture then of fuel and sorbent fall directly down this central chute into the DFM mill located directly below. Multiple fuel outlets, as shown here, allow uncomplicated fuel splitting. A combination of coal and limestone therefore then land in the center of the DFM system, landing on a feed tray supported by the spider. The solids are spun off centrifugally into the upward rising airstream. Pre-sizing takes place at this point, and material that is already to size is caught up in the airstream, thereby bypassing the grinding elements. This pre-stripping of product helps minimize oversized grinding and the generation of extreme fines, and results in lower horsepower per ton. The coal is crushed entirely by rolling contact between the roll and bull ring. For a circulating fluidized bed combustor, this is the world's first direct firing fuel preparation system. The Williams ring roller mill direct firing approach gives excellent control over particle size analysis, coupled with drying, mixing, and distribution of the fuel and sorbent. The vertical shaft is driven by means of an external right-angle gearbox and drive motor through couplings. The motor is connected to a variable frequency drive so that the vertical shaft speed can be varied from 0 to 100% speed. With the bottom discharge as shown here, beneficiation can be incorporated with the removal of impurities, pyrite or tramp metal, and this is accomplished with the bottom mill discharge. Automatic lubrication is accomplished while the system is running. Multiple outlets can be supplied so that even distribution of coal can be made to the CFB. Due to the rotational speed of the DFM mill, the swirl imparted to the rising air through the windbox area, and the limestone and coal particles are evenly mixed and transported to multiple outlets.
The two DFMs, and is split into 4 sections, one to each of the side walls of the combustor. The coal is very, very simple. It comes up and is blown in essentially at the end of a pneumatic pressurized pipe. It's blown in on a slight negative dihedral so that it promotes mixing with the upcoming fluidizing air coming off the grid down below.
For the purposes of obtaining a representative sample, a typical cyclone coal sampler is utilized on the outlet duct.
The D50 is now 934 microns. So it's basically laying right in here on this material. Nice, coarse, granular material. These are the fines, 18 mesh, 50 mesh, all the way down to the 100 mesh shown here. And this is minus 100 mesh. And there's only 11.8% minus 100 mesh with a D50 of 934. maximum continuous rating. The air coming in, 964 degrees. The set point's 974. Middle delta pressure is 8.1. Design is 8.0. 91% full load amps. Bed temperature is 1611.
The sludge is pressed and majority of the water removed. The sludge then is transferred by belt conveyor up to a surge bin where the sludge is metered into a conveyor system, and the conveyors then transport the sludge to the boiler building.
This is a picture of the in-feed conveyor for the de-inking sludge from the press building. This is the largest volume of recycled sludge burned anywhere on the face of the earth. This boiler is rated at 46% MCR on just de-inking sludge. Most units hold 4, 5, 6%. This one is obviously the largest made. What we're looking at here is fluffed materials that is about 55% solids. This is the bottom of the cyclone where it comes into a non-mechanical loop seal, which is essentially a U-tube manometer. From there it is additionally fluidized with 100-inch air for these lines you see here. And then it mechanically goes back up, which is part of the U-tube manometer effect. And then it slides over a hump and goes down into the bottom of the combustor for the final recycle. Otherwise, the pressure from the furnace would blow back up through here and would not have a differential pressure seal with the cyclone. What you're looking at here is the sludge feed points coming in by mechanical conveyor from the sludge press house next door. It's fed in and is evenly divided into the two loop seals. The hot return material coming back from the cyclone is coming down through this loop seal at about 1560 or 80 degrees. And at that point, the sludge is laid on top of it to promote immediate heating, drying, and mixing with the hot recycled material. This is the secondary air inlet, which is used to pick up some heat by natural convection, conduction, and radiation off of the upper portion of the bottom ash hopper, which does not have a water-cooled screw. This is the first installation in the world without one. As you can see, it's not required, and the air is picking up only a very, very small amount of heat and is conveying that heat along with secondary air through this duct over to the inlet of the secondary air fan. This is all very conventional pneumatic ash pickup material where the hot solids out of the bottom of the combustor, the rejected solids inventory, is conveyed pneumatically out to the ash silo for disposal in conventional pneumatic fashion. An example of the coarse material that would come from the bottom ash drain on the combustor. As you can see, it's fairly small material.
The ash is pneumatically conveyed to the top of this storage hopper, where it is removed at the bottom by a conventional dump truck to landfill.
The building on the right-hand side behind the rail cars is the turbine generator room. Coming across is the power plant offices and control room, which is just beyond the transfer tower for the sludge and the coal. Then is the circulating combustion boiler by Pyro Power, which has the elevator here on the outside, its extension. Then to the rear of the building is the entrance to the Savinska Flak-Fabriken rigid frame precipitator, followed by the ash handling system and the large circular silo on the far side, the tan silo, and then the bricks chimney for the unit.
This is the steam generator building where a 48 megawatt steam turbine and generator is utilized to provide part of the energy utilized by this plant.
The big object on the right is a HRSG heat recovery steam generator. Has its own stack, of course. It's connected to a 40 megawatt General Electric gas turbine, which on the left-hand side, the tan part on the left-hand side, are the inlet filters for the gas turbine. Has a bridge crane over the turbine. And it is connected electrically through the proper distribution grid to the steam turbine, which is the building further to the left, just behind the switch yard, the gray short building in front of the boiler. These two turbine generators provide most of the electric power necessary to run this paper mill, which makes it essentially electrically self-sufficient, or energy self-sufficient for that matter. They have to buy coal. They mix the coal in with their own de-inking sludge. The de-inking sludge has a net heat contribution to the steam generation process in the PyroPower circulating fluid ice combustion unit. Therefore, Southeast Paper is utilizing waste material, landfill material, to generate steam, to produce energy, to run this plant. The entire plant runs off of recycled waste paper, so this is really an environmentally friendly paper mill.